Now let's venture into matrix multiplication. We'll start with the inner product, which is the multiplication of two vectors, a row times a column. Now, one notation that I haven't pointed out yet is this transpose operator. As I mentioned previously, in linear algebra, we tend to assume that all vectors are by default a column. The transpose operator takes a matrix or a vector and transforms it from a column into a row. In the case of a matrix, the transpose of a matrix is a new matrix where all of the rows are the columns of the original matrix. This inner product is often referred to as the dot product in physics. The result of the inner product is just a single scalar. The formula for the inner product is the sum of the product of corresponding elements. Now, in my brain, visually, this animates something like this. The purple vector is picked up, placed on top of the green vector. Multiplication is done going down. Addition is performed going across, resulting in this red scalar. Obviously, in order for this to work, I need that red and green vector to have the same number of elements. If the two vectors do not have the same number of elements, this operation is not defined. Now, we can use the inner product to define matrix vector multiplication. So here I have a green matrix and a purple vector. And when I multiply this green matrix times this purple vector, what happens is that purple vector, in my view, gets picked up, put on top of the matrix, and the sizes here must match up. So I must have the same number of elements in the vector as columns in the matrix. And this vector just kind of moves through each row of the matrix, forming inner products at each step. So here, that is multiplication happening element-wise, and addition is the arrow moving across. So there's an inner product here of that purple vector with every row of the matrix, making the result a vector that has the same number of rows as the green matrix. Now, we can also view this matrix vector multiplication as a linear combination. This is potentially more important to see because it has implications in the tools that we will use. So if you just look at an example of that multiplication we just did, what's happening in essence is this purple vector, the elements in that purple vector are forming a linear combination of the green columns, resulting in the red vector. Now, the easiest way to see this is to draw a quick example and see how we can pull out those scalars from each column. When we multiply two matrices, what we're doing is really just a collection of matrix vector products with different coefficients. So here, this matrix A is 4 by 3, 4 rows, 3 columns. B is 3 by 4, 3 rows, 4 columns. and the resulting vector is 4 by 4. So when we first learn matrix multiplication, it's very common to write out the dimensions of A and B here, confirm that their inner dimensions agree, meaning the number of columns in A and the number of rows in B. And then the resulting matrix will have the dimensions as the rows of A and the columns of B, those outer dimensions. Before we get into that linear combination view, let's just talk about the basic definition of matrix multiplication. And that is that the ijth element of the product is equal to, and here's some new notation. This star can be taken in your mind to read all. So the ith row, all columns. So that's talking about the whole ith row of A. Here, I have all rows in the jth column. So that would be the jth column of B. So this formula here is saying that in order to get the ijth element of the product, I multiply the ith row of A by the jth column of B. Okay, the example here is the 2, 3 element of the product, so I multiply the second row of A times the third column of B. So this is telling me that in order to get this product, I would just take every row of A and multiply by every column of B to carve out these individual elements of the product. But what will help us more in our applications is to learn to view matrix multiplication as a series of linear combinations. The first fact is that in order to get the first column of the result, I multiply the matrix on the left, A, the green matrix, by the first column of B, the purple matrix. Now, in light of what we have learned before, this means that the first column of the result is a linear combination of the columns of A, which is the first matrix, with coefficients coming from the first column of B. Now, one of the reasons why this is so important is because it's true for every column of the result. Second column is given to us with the linear combination of the same vectors, those same green vectors, with new coefficients. Similarly for the third and the fourth. Now, one of the reasons why this is important, and I'm just going to try to allude to a bigger picture here, is that we're taking a collection of elements, being the vectors in the result, and we're expressing them as a breakdown into parts. All of them will be broken down into the same set of parts, but with different weights. And so this is essentially what we'll try to do as we move through the fall, is interpret this type of matrix factorization where we try to interpret what these parts mean and also what these weights say about the individual objects. So again, this linear combination view of matrix multiplication is probably the most important thing I will teach you in this 90 minutes or in the primer. You have to also realize that matrix multiplication is not commutative. AB is not equal to BA in linear algebra. In fact, it's possible that AB is legal and BA is not even a legal multiplication, meaning it's undefined because the dimensions of B and A are not conformable to multiplication. By that, of course, I mean that these dimensions don't line up. Okay, so if those dimensions don't line up, then it's not even possible to multiply A and B. Matrix multiplication is just a collection of matrix vector products with different coefficients. Each linear combination involves that same set of vectors, those green columns with different coefficients. This is just summarizing what I said on the last slide. And this has important implications, as I tried to allude to. In the next video, we'll cover some more matrix operations and special matrices.